Okay, now that we know how to apply implicit differentiation, we will use that to go ahead and determine what the derivatives of the inverse trig functions are. So when you were back in trigonometry, you learned about inverse trig functions, which are sometimes written with the little kind of the -1 power, or sometimes they're replaced with the word arc, A-R-C. So if they say find the arc sine of something, they mean the inverse sine of something. So all of these are inverse functions. And so this, just to make sure, this does not mean the reciprocal of 1 over sine. The reciprocal of sine is cosecant. That's different. This does not mean the reciprocal, this means the inverse function of these trig functions. So that's a notation issue. Let's go ahead and figure out, how can we figure out the derivative of these? So if we have this function, let's say, recall this function y is equal to the inverse sine of x. The inverse sine, just as a reminder, inverse functions are functions that pass the horizontal line test. Remember that? So here's a sine wave, basically, right? Here's a sine wave. This does not pass the horizontal line test. It fails it terribly. It fails it infinitely many places. And because of that, they said, let's look at a sine wave only from this section to this section. They pick a section of the sine wave that would make it pass the horizontal line test. And so they said, let's take it from here to here so that we capture all of the outputs, all of the range of this, but that it doesn't hit more than once if you pass a horizontal line through this. And so this is from -pi over 2 to pi over 2. That is the portion that we're looking at right here. Okay, so what we're saying is, what angle would give us an output of some angle? That's what we're asking when we look at the inverse sine. So if you recall that this is values, -pi over 2 to pi over 2 is what we're looking at right here. Okay, so let us begin. Just as a reminder, if you had this function here, you could apply an inverse function to sine is sine inverse, but an inverse function to sine inverse is sine. So if we look at this, what if we say, let's find the sine, let's take the sine of both sides. What would happen here? Then on the left we'd get that the sine of y, the sine of sine inverse is just the inverse. It's just, you're just going to get, these undo each other. You just have x, basically. You can apply sine to both sides and get this. Okay, what are we trying to figure out here? We're trying to figure out the derivative of sine inverse. If y, look at the black part, y is equal to sine inverse, what we're after is, we're trying to figure out, trying to find y prime right here. We're trying to find y prime right there. That's what we're after. Well, you know what we can do is we can take this equation and find dy dx, we can take d dx, the derivative, with respect to x of both sides of this. And then it will help us solve for this derivative of inverse sine. So here we go. The derivative of sine with respect to y is, the derivative of sine is cosine, so it's cosine of y, right? But this is chain rule, y is a function of x times y prime. What is y prime? Y prime is what we're trying to figure out here. Y, right? Y is the sine inverse of x, that's what it is. Over here, the derivative of x is just 1. So y prime is equal to 1 over the cosine of y. Okay, there, we did it. That's what y prime is, but let's put it in terms of x. So what we need to do here is draw yourself a right triangle. Okay, remember right triangles and the trig functions? Let's say y is going to be our angle right there. Okay, and so what do we know here? Let's look at this. Look at the blue part right here. This helps us draw our triangle right here. Draw your triangle off of this information. It says that the sine of y is equal to x. the sine of y is equal to x. But the sine is always opposite over hypotenuse, And so once we have a right triangle and we know these two values, we can solve for the adjacent side using the Pythagorean theorem. This is going to be the square root of 1 squared minus x squared. Okay, that helps us draw our triangle, and that helps us write y prime in terms of x. So y prime is equal to 1 over the cosine of y. What's the cosine of y? It's adjacent over hypotenuse. It's the square root of 1 minus x squared over 1, or just this. So this is what y prime is, but what was y in this case? It was sine inverse. So we have our first answer. The derivative of inverse sine is 1 over the square root of 1 minus x squared. This is how you can derive the inverse sine derivative. I'm going to do another one. I'm going to do tangent. Cosine is very similar. I'm going to do tangent just to show you how this works, and then we're going to do some examples. Let's see here. What if we had to find the derivative of tangent? What would it look like? Okay, let's do that one. So this is what we know. There is a function that exists called the inverse tangent, and they did the same thing with tangent that they did with sine and also with cosine, is they restrict the domain of that function so that it passes the horizontal line test so that you can find an inverse. So that's all good. So let's look at y is equal to the inverse tangent of x. This is a function of x. Okay. If we want to find his derivative, this is the way to derive it. We can simply take the tangent of both sides of this. So if we take the tangent of both sides of this, let's see what we get. We get the tangent of y is equal to the tangent of the tangent inverse of x. And so the tangent of the tangent inverse undo each other, and we just get x right here. Okay. So the job is to find, this is what we're after, d dx of tangent inverse of x, or basically y prime. What is y prime? What is y prime? But this part in green, this is what we're going to use, like in the last example where we drew a triangle. This is what we're going to use this to draw our triangle. We could go ahead and draw our triangle. Here's our right angle. This is the angle y, and it says that the tangent is equal to x. We know tangent is the opposite over adjacent, and we can use the Pythagorean theorem to figure out the rest. So the hypotenuse c squared, c is going to be the square root of a squared plus b squared. This is what the tangent is equal to. Okay, so we drew our triangle, that's fine. Now let's go ahead and find what dy dx is using implicit differentiation. So let's do that. Take d dx of both sides of this. All right, the derivative with respect to x. Okay, the derivative of tangent is equal to, and hopefully you know this by now, the derivative of tangent is secant squared. So it'd be secant squared y, chain rule, times the derivative of the inside, y prime, is equal to the derivative of x, which is just 1. So now we solve for y prime, which is 1 over secant squared of y. At this point, you would draw your triangle, but we already did that work, so let's figure this out. Well, 1 over secant squared is really cosine squared, because secant is 1 over cosine. This is really cosine squared of y. This is what this is equal to. Okay. Well, what is the cosine? Cosine is adjacent over hypotenuse, but it's being squared. So this is equal to 1 squared, which is 1, over the square root of something squared, which is just the something. And we find that y prime is equal to this when y is the tangent inverse of x. And so we find that this is equal to 1 over 1 plus x squared. Now, you see the method. You could go through and do all of these. In fact, one of your homework problems has you doing this method that I just showed you. But you can also, it's a good idea to memorize these. This is what the derivative of cosine inverse is. It's negative 1 over the square root of 1 minus x squared. The cotangent inverse, the derivative of him is negative 1 over 1 plus x squared. Secant x, the derivative of secant x is 1 over x times the square root of x squared minus 1. And the derivative of cosecant, the inverse cosecant, is negative 1 over x times the square root of x squared minus 1. Now, I didn't used to make students memorize that, and I don't know how I can force any of that in an online class, but I will tell you, I've watched many Calc 2 teachers, and they just say, hey, do this, and you need to know this, So you're not doing yourself a favor if you don't get really familiar with these, because it will just be painful for you in the next class if you're not really familiar with these. I'll just put it that way. So if you went ahead and memorize these, that would be doing yourself a favor. Let's just see, there's some similarities you can pick up for memorization. Remember how the derivative of sine is just cosine, but the derivative of cosine is negative sine. How when you're taking the derivative of a cofunction, there's always that negative involved. The same thing is going to apply here. Do you see the difference in the derivative of sine inverse and cosine inverse? They are the same, except for that guy's got a negative. Between tangent and cotangent, they are the same, except for cotangent has a negative. Between secant and cosecant inverse, they are the same, except for cosecant has a negative. So that's going to help if you're trying to memorize these guys. All right, now we're going to use these. That was how you come up with them. Let's do a few examples that involves differentiating. So these are not that long, so it's not going to take too long. You guys are going to be fine. Example 1 goes like this. As soon as I erase this board, and then I'll be ready for example 1. The green is hard to erase. All right, here we go. Find dy dx by implicit differentiation. Now we know what that is, and so they ask us to find dy dx for this function, the tangent inverse of x squared y is equal to x plus x y squared. Okay, implicit differentiation is the process of taking the derivative of both sides and solving for y prime. So that's what we're going to do. D dx over here, d dx over here. All right. The derivative of inverse tangent is, you memorize it, you come up with it. Somehow you're going to figure out that it's this. All right, fine. So the derivative of inverse tangent is 1 over 1 plus x squared, but x squared has been replaced with this function, this expression, x squared y. So this is chain rule we're looking at. So it's the derivative of inverse tangent, which is this, times the derivative of, we have something that's not just x, times the derivative of this. Okay, this is product rule. So this is times first, times the derivative of the second, y prime, plus second, y, times the derivative of the first, 2x. All of that is what it gets multiplied by, if you want to put that over 1. Or you could have even put it just in the numerator. Times the derivative of this side. Derivative of x is 1 plus, this is product rule, derivative, it's first, times derivative of the second, 2y, y prime, plus second, y squared, times the derivative of the first. So, what we have here is to solve for y prime. So let me just clean this up a little bit. This times this, we'll just put this part in the numerator. So let me do that. 2xy. Okay, that's really what I have on the left. Now what I'm going to do is I'm going to kill my fraction by multiplying both sides by this denominator. So this is really 1 plus 2xy times y prime plus y squared there. That just cleaned that up a little bit. Now I'm going to kill my fraction by multiplying by the denominator on both sides of my equation. 1 plus x squared y squared is going to be x squared squared, which is x to the fourth, y times y to the 1 raised to the second power is 1 to the 1 times 2 y squared. 1 plus x to the fourth y squared. If I multiply this by this side, these will cancel. I'm left with x squared y prime plus 2xy is equal to 1. I'm going to distribute this. 1 plus 2xy times y prime plus y squared plus x to the fourth times each of these plus x to the fourth y squared times 1 plus 2xy, y prime times x to the fourth times y squared is 2, x to the fifth, y to the third, y prime plus y to the fourth, y squared times this is x to the fourth, y to the fourth. Okay. Now, what are we going to do? We're going to get all of our y prime terms on one side, everybody else on the left, on the right, I mean. So y prime, I'm going to factor as I go. I'm going to factor out y prime. I'm left with x squared. If I subtract this guy over here, it's going to be a minus 2xy y prime. If I subtract this guy over here, it's going to be a minus 2x to the fifth y to the third times y prime, leaving me with 1 plus y squared plus x to the fourth y squared plus x to the fourth y to the fourth, and plus I'm gonna subtract this guy over here, minus 2xy. To solve for y prime, I'm just going to divide both sides by x squared minus 2xy minus 2x5 y3 . So this is what y prime is. There was a little bit of calculus and a whole lot of algebra in that problem, and that is kind of how calculus goes sometimes. Okay, let us do another example. It says find y double prime for this one. Okay, let's see. What is this one? It is the sine of y plus the cosine of x is 1. Sine of y plus the cosine of x is 1. Example 2, the sine of y plus the cosine of x is 1. All right, so we need to find y double prime. That's our job. Second derivative. Find y double prime. Okay, so first let's find y prime by taking the derivative with respect to x on both sides. So let's do that. d dx of this side, d dx of this side. Okay, the derivative of the sine is cosine. So this derivative, this first term is going to be the cosine of y, but y is a function of x times y prime. That's chain rule. Plus the derivative of cosine of x, which is negative sine x, or if I just want to say just here, minus sine x, that's fine, is equal to the derivative of 1, which is 0. So y prime, the cosine of y times y prime, is equal to the sine of x. When I add that to the other side, I can divide both sides by cosine of y. I get y prime is the sine of x over the cosine of y. This is y prime. All right, we got to find y double prime. So what we're going to do is take the derivative of this right here. All right, so y double prime is, this is quotient rule. Low cosine of y. D high, derivative of sine is the cosine of x. Minus high sine of y. D low, derivative of cosine is negative sine y times y prime, there's chain rule, all over, let's see, low d high minus high, ooh, there's a mistake, high d low, okay, all over low cosine squared of y. Okay, that's the derivative of y prime. So this is what we have. We have the cosine of y times the cosine of x, minus is a plus, the sine of x times the sine of y times y prime. What is y prime? Right here. This is it. Times the sine of x over the cosine of y all over the cosine squared of y. All right, now we can clean this up a little bit by getting rid of this complex fraction by multiplying by the lowest common denominator that I see of the little denominators, which is right here, cosine of y. So if I multiply this top numerator and this denominator by the cosine of y, it's going to clean up my complex fraction, times the cosine of y. All right, what's that going to do? It's going to distribute to both sides, both terms. Cosine of y times this gives me the cosine squared of y times the cosine of x. Right there. Cosine squared of y times cosine x. Plus, what's it going to do here is it's going to cancel this. So I just get sine squared of x plus sine squared of x times the sine of y times the sine of y. All right, all over cosine squared y times cosine of y is cosine cubed y. So that is the second derivative of that function. All right, now let's see what we have left to do. This one's pretty easy. Example 3. These last two go real quick. I know you're like, oh my goodness, this is taking forever. But these last two go really quick, so hang in there. We're almost done. Example 3 goes like this. Oh my goodness, there we go. Example 3 goes like this. Find the derivative of the function, simplify if possible, and so they give us this function right here. Y is equal to the tangent inverse of x squared. This just is going to be so simple compared to what we've already been through. What's the derivative of the tangent inverse? Well, we derived it pretty early, but we can just look at our chart right here. It's 1 over 1 plus x squared. That's if your function's x squared. Our function's a little bit more than x squared. I mean, if our function is x. Our function's a little bit more than x, it's x squared. But that won't be too hard to deal with because we had a more complicated one the first example that we did. So, y prime, right here, y prime, is going to equal to 1 over 1 plus x squared. But our x is not x, it's something more than that. It's x squared. So this is the derivative of that. This is 1 over 1 plus x to the 4th. Oops, I forgot chain rule, so let me try again. Okay. Y prime is going to be 1 over 1 plus x squared, or 1 over 1 plus x squared squared, that part's fine, times the derivative of the inside function. What is the derivative of x squared? It is 2x. So this is going to be 2x over 1 plus x to the 4th. That's what the derivative is for example 3. Here is example 4. Goes like this. Find the derivative of the function, simplify if possible, and they say g of x is equal to arc cos the square root of x. Okay. Remember I mentioned that earlier, that arc is another way of writing inverse. So this means the inverse cosine. How do you find the inverse cosine, the derivative of the inverse cosine? We could derive it, and you might have to in your homework, but this is what it equals to, okay? That's if your function is x, but ours is not x, ours is square root of x. So a little bit of chain rules involved here. So g prime of x, and if it helps you, if the arc notation is bothering you, just rewrite this into this. However your mind likes it, just rewrite it in a place that makes it happy for you. Then take g prime of x, so g prime of x, the derivative of the inverse cosine is 1, or negative 1, over the square root of 1 minus x squared. But our x is the square root of x. So we put that in there. Times the derivative of the inside function. Times the derivative of the square root of x. So at this point, let's remind ourselves that the square root of x is really x to the 1/2, right? So the derivative of the square root of x will be times 1/2 x to the negative 1/2. So we can clean this up. This is going to be negative 1 over 2 is in the denominator. Square root of x is in the denominator. And then we have the square root of 1 minus the square root of something squared is just a something, x. We can write it like that. We can write it like this. There's a rule that says the square root times the square root. You could multiply these two things together. The square root of x minus x squared. That could get distributed in there. But that is the derivative of g of x.